reached our last speaker, Mr. Kian, who will speak to us on a new local approach to cleavage fracture and to application in a reactor pressure vessel.
So, thank you very much for the kind introduction. Good afternoon, ladies and gentlemen. My name is Yuan Chan from the Institute of Mechanics, Chinese Academy of Sciences. So, I'd like to introduce you a new local approach to cleavage fracture and its application in reactor pressure vessel. So, my collaborator is Dr. Lei, Zhu, Korea, and Jesus. So, in my talk, I will introduce the following 4 parts. The first part is a brief introduction to a local approach to fracture. And then I will pay a very brief visit to Brahmin model. And in the third part, I will present a new local approach to fracture. And the last, I will draw a conclusion. So, as we all know that electrical skills are widely used in engineering applications, such as in a reactor pressure vessel in nuclear power plant. Due to the PCC structure, the material is very demonstrate ductile to brittle transition. So the material is very susceptible to brittle fracture. And fracture toughness is the parameter to describe brittle fracture. However, substantial studies show that fracture toughness demonstrate also a size effect, temperature, and irradiation effect. Here we can see that even tested at the same temperature, that fracture toughness varied significantly. So, in order to statistically predict fracture toughness, there are generally 2 methods. One is a mass curve method, which has already been standardized in ASTM standard. And the other one is local approach to fracture, which is the focus of my study. So the goal of my study is to propose a new model and try to calibrate and to apply this method for some engineering application. So in order to study local approach to fracture, let's start from Brahmin model. So according to Brahmin model, the brittle fracture is start from crack initiation from the homogeneity, such as cracks and grain boundary, and then crack propagate until lead to a final failure. According to previous equation, it correlates with the critical stress with the critical crack depth, as shown in this equation. And in this local approach to fracture, the micro crack size distribution follows the Taylor law. Here, F and beta are the 2 parameters to describe the distributions. And then for an small element, the fracture probability is shown in this equation. Here, this shows that the probability of fracture is the probability to find a crack, which is larger than the critical crack depth. But here, we should be noted that the upper bound here it takes as infinite value. And then, according to the weakest link theory, which means that the weakest part of the material determines the strength of the material. And here in the structure, there are a lot of these small elements. There are a lot of small volumes, and in each volume, the crack, there may be a crack, and the crack follow a tolerance distribution. And then, following this procedure and the probability here takes some approximation here, log n 1 minus PF, it assumes to equal to minus PF, and then finally the fracture probability of the whole structure is equals to this equation. Here, sigma W is the Weber scales, and M and sigma U are material property. One is corresponding to crack distribution parameter, and the other one is corresponding to microscale fracture stress. And then, let's say, in order to apply this method for engineering application, so we need to calibrate these 2 material property, M and sigma U. Here, well, recently, a lot of studies tried to calibrate and found some difficulty. One thing is that they found these 2 parameters, they will change both with geometry and also with temperature. Here we can see with different geometry, and then here we can see this M will change, and also with different temperature, M and sigma U both will change. So since, as we mentioned before, M and sigma U, they both will be material properties, but they are changed now, so it's very difficult to calibrate, and for engineering application, then this is a big problem. So this raises questions. What could be wrong? Is the Brownian model itself is wrong, or the calibration method is wrong? So then, in addition, we also analyze the extension of this Brownian model. Following this Brownian model, there are also some modifications, such as Gauss model and the ASTM model, which is the so-called mass curve method. And according to these two methods, they try to introduce the threshold for brittle fracture. Because for the brittle fracture, they argue that there should be a threshold. Well, for these two models, the threshold are assumed to be a constant, sigma th or K mean. Well, if we analyze three cases, one is smooth specimen, one is specimen with a notch, and the other one is cracked. We know with these three specimens, the stress reactivity and are different. Well, the initiation threshold and also will also change with temperature. So in this sense, this sigma th cannot be constant. It should be changed with temperature. Also should be changed with the stress reactivity. That is the constraint of the practice. So then, we know that there are some problems with Brownian model, so we go back to the Brownian model again to try to see what's wrong. So in Brownian model, we see that they make some approximation here. Log 1 minus PF equals to this minus PF. And then for these assumptions, we take another revisit, and we calculate these two terms. And here we show that when the probability PF is quite small, and then these two terms, they are equal to each other. But if the probability is larger than a value, then there should be a big difference. So this somehow is a limitation. And the other limitation is the upper bound of the integral. Here it takes as infinite, according to Green's equation. And here, if FA corresponds to infinite, that means the stress will equals to 0, then there will not be brittle cleavage fracture. And also there are three cases in this for beta value, and here in Brownian model it only takes 3. So we know there are 3 limitations with Brownian model's assumption. So then we try to propose our new model log approach to fracture, but also according to the weakest link method. And here we follow a very strict mathematical subroutine. And here the upper bound we take a limit A max, and also for this FA we can also convert to the flux strength of element, and we assume that the flux strength follows a 3-parameter Weber distribution, and finally we can get the probability of the whole structure. Also is similar to Brownian model, but here we introduce some threshold, and this threshold will change with temperature, also will change with corrective constraint. So we have now our own model, so we also have to calibrate it before we can apply for engineering application. So in order to calibrate it, here we take that 2 times logarithm, and we can see that PF and sigma W here, it follows a linear regression. And then we use this linear regression method for the calibration. And we take a monocolor simulation, and we assume an initial M0, and follow this simulation we can calculate another M0, and if they equals to each other, then this is the final result. And for the finite element method, we use 3-dimensional finite element method, and we wrote our own subroutine to calculate Weber stress distributions. And then this shows our calibrated result. Here, in general, they are temperature independent. Well, this is different from the study in reference. Here shows they will change with temperature. So this proves that our model, this material property, are temperature independent. This is our advantage. Also here, if we plot a function of P versus the nominal strength at a different temperature, we can also see that they fall into almost the same curve. It also proves that the advantage of our model. And also, our model is also validated, calibrated with this Euro toughness databases, which is for reactor pressure vessel. And the similarity here, different temperature, we can also see this curve for almost in the same curve. This also confirms that the advantage of our model is that these two parameters, they are temperature independent and can be calibrated for further applications. And then for further application, as we mentioned, in nuclear power plant for reactor pressure vessel, the toughness normally is tested and calibrated for different kind of specimens. And from small specimen, CT specimen, 3-point bending specimen, and cruciform specimen. So how to transfer this toughness? So we use our model to transfer this model. And after calibrating the material properties. And here we can analyze at the same K, we can analyze the vapor scales. And here we can see is a difference. And also we can see the same K and analyze the fracture toughness. And we can see because of the constant effect, and it shows a big difference. And by using our model here, we can quantify this practical constraint effect, and also can use this method to transfer fracture toughness between different specimens, as shown here in this figure. So I would like to summarize my talk. So a new local approach to fracture presented, calibrated, and applied in transfer K1C between different specimens. And the proposed calibration method proves temperature independence, and it is a mass curve correlation between for cleavage in notch and cracked specimens. And for further application of our model in other components, you could also refer to my Google Scholar and for other information. Thank you very much.
Okay, I'd like to, we actually do have time for questions, but I think it would be unfair because only one person maybe would ask a question. So since it was not planned to have Since it wasn't planned to have any questions, we'll stop at this point, but I want to thank all of our speakers, and they make me feel really good that fracture mechanics, fatigue, and structural integrity are in good hands for the future. Thank you.